Hey guys, in this video we're once again going to be discussing the force that wires exert on each other due to the fact that they both make magnetic fields and currents experience a force due to magnetic fields. However, we're not going to be looking at two long straight wires in this particular video. So here's our scenario. We got one current which is up the page and another current which is in a rectangular loop, and it looks like it's going in the clockwise direction. Okay, so the question is going to be, does the loop attract towards the long straight wire, or is it repelled from it? Now for these problems, they'll also usually, if they want you to make a calculation, give you some dimensions here. So we're going to say that the width of the rectangle is A, the length is B, and that the near edge of it is a distance of C away from the straight wire. Now, the first step in answering this is to draw the magnetic field that the long straight wire is producing over where the rectangular loop is. Now, if you don't understand why the x's are there, you should do your second right-hand rule to figure out where the x's came from. And you should discover that if your thumb is pointing up the page, then your fingers, as long as your hand is pointing off to the right of the wire where you're looking for the field, your fingers are pointing into the page. So thus, the x's. Now, you should notice a couple of things at this point. Number one, the current in that rectangular loop on the left side is going up the page. Okay, now you could then use your first right-hand rule and IL cross B to figure out the direction of the force on that side. The right side is, of course, carrying current in the opposite direction, and you could also use the right-hand rule for that side. Now, it should be immediately obvious that those two forces are going to be in opposite directions. All right, now I'm going to table the question of what the directions of those various forces are for the moment, because I want to have you consider something important. While those two forces, whatever they are in opposite directions, they are not equal. And this is a very important fact. Wait, but why wouldn't the two forces be equal? Well, the reason the forces aren't equal is for the simple reason that the magnetic field on the left side of the loop is of a different magnitude than the magnetic field over here on the right side of the loop. And that's just because one side of the loop is closer to the long straight wire than the other. And as we know that B is dependent on the distance from the wire, since R is going to be different for those two sides do not experience equal forces because they are in different magnitude magnetic fields. All right, now let's try and next answer the question of which direction that loop is going to ultimately be pulled in. So to answer that, we need to figure out the direction of the force on each side of this loop. Now, I neglected before to mention that the top and the bottom also experience forces. Those two forces will actually exactly cancel out. But go ahead and take a moment, pause, use the first right-hand rule, figure out the direction of all four of those forces. And this is the result you should get. Now, this is going to be a fairly common thing that you'll see is all the forces, say, go out from the loop. Had I given you a different scenario where the current went, say, counterclockwise, we would have gotten the exact opposite result here. We would have had all of the forces point inwards. So it would have been like that in that event. Okay, now the next question, or really part of the same question is, okay, so fine, all the forces point out. Net, which way is that rectangular loop attracted to? Is it, or repelled, right? Is it attracted to the left or is it repelled to the right? So it depends which of those forces is greatest. Well, we said these two forces, the up and down, those will exactly cancel out. But the left force and the right force are of a different magnitude. So pause me again, think about which of those fields is larger, and therefore which of those forces is larger, and you should therefore be able to have the answer. And everything hinges on this idea. Since the magnetic field follows this function right here, the greater the distance, the smaller the magnetic field. And since the force is given by the equation IL cross B, if you have a smaller field, you have a smaller force. So that means that the right side should experience the smaller force. If the force on the left side is greater than the force on the right side, then the net force is going to be to the left. Okay, so net, that loop will be attracted. All right, now what if we wanted to actually calculate what that force is? All right, well, let's see if we can set that up. Obviously, if we want to calculate the net force, we have to calculate the two forces that make the net force, so the F left and the F right. Both forces follow that equation, but I do have one difficulty in notation here, and that's that this B1 and this other B1 aren't the same B1. I mean, it's the magnetic field produced by current number 1 in either case, but one of them is referring to the magnetic field here, and the other one is referring to the magnetic field there. So in the next line down in the algebra, I've resolved that particular problem by calling one distance R1, that's the distance to the left side, so that'd be the smaller distance, and the other one I'm calling R2. All right, well now all that I got to do is plug in values, if I had values. In this case, I'm going to plug in letters, and so we'll end up with an expression that we could plug values in for if we had them. All right, now first thing is the length of the wire is this dimension here, which is labeled as B. So that's going to be the same for both of those terms there. Okay, so thus I've labeled L is going to be replaced with the letter B. R1, that's the distance to the left side. That is, as you can see from the diagram, just C. And then R2 is the distance to the right side of that rectangular loop, which is going to be A plus C, whatever those are. So putting it all together, I would have this, which, I mean, that looks like a hot mess, but, you know, if you had values, you could plug it in and you'd have nice numbers. If we didn't have numbers, or, frankly, if you're looking for a simpler way to make your calculations, we can actually very cleverly factor out all of the things that are in common in between those two terms, and then have in parentheses whatever remains. Okay, so if you like, take a moment, see what you can factor out. Pause me, resume when you're ready. Okay, so that may not look any nicer to you, but it would be much easier to calculate, right? You'd only have to plug in these values here once and then multiply it by whatever this is, as opposed to the other way, which involves plugging things in many times into your calculator. And the more things you have to type, usually the worse your odds are of getting the actual correct answer. So I like this way better. Factoring helps us simplify the calculation. All right, well, that being our final answer, let's put a box around it. Now, before I close this video out, the last thing I wanted to mention was going back to what if we had a current that was going in the opposite direction? What would we do differently? Well, really almost nothing. The thought process would be identical, right? This line in your work would be the same, basically the same, and nothing really would change. The only real difference actually would be that when we wrote our answer, we would say to the right as opposed to the left. So this answer here is to the left. Remember all that analysis we did? All right, if we had instead a counterclockwise current in our rectangular loop, then the final result would have been to the right. Okay, well, that's everything. I hope that helps, and thanks for watching.